In this section now, we are ready to talk about functions of several variables. So we're going to actually start doing calculus on functions. What are we going to do? We're going to start with functions of two variables. For example, this is a function of two variables. In this case, this would be f of x and y is x squared plus y squared, and that is the graph. We're going to try to understand what's the domain and the range of a function. We're going to try to figure out how to do graphs of functions. We have some basic understanding of what the graphs of quadrics are, so we're going to use that. But then there's going to be we haven't seen yet a logarithm or a sine or a e to the something. There's going to be more and more complicated functions, and we're going to have to use different things to graph it. And what we're going to do is level curves. Just like we were doing cross sections of quadrics, we can do cross sections of anything. Any graph, I can cross section it, try to see what is happening. Sometimes the graphs are so complicated, I don't know how to graph it, but in some specific problem, we're interested in what is happening around the point 3,2. 3, and then I can do some cross section that goes through that point, and I can try to understand what is happening exactly at that point. And then this is multivariable. This is not two variable. It's multivariable calculus. So we're going to start to look at functions that have more than two variables. Why do we complicate our lives with more variables? Most functions, most things that we try to model in nature, in economics, in biology, in medicine, they do not depend on one variable, they depend on several variables. For example, wind chill. You want to know when you are at danger of frostbite. That is a function of two variables, the temperature and the wind speed. I have here a chart by Noah on, this is so the x values are the temperature in Fahrenheit, and the y values are wind speeds in miles per hour. And this is just a chart of some values of the function, but the function itself, of course, like we can know what happens when the temperature is, I think today was 6 degrees. What is the wind chill, depending on the wind? What's the actual temperature you feel on the skin? It's somewhere in between here. It's not in this table because this is just a table, because the function is complicated and you don't want to give the general public this function. So this is the actual function in Fahrenheit and miles per hour. This is the function of two variables. The temperature that you feel depends on the temperature and the speed, like this. And you can see it's like some fairly complicated function. And I do have it somewhere, so let me show you the graph. This is the graph of the wind chill. Okay, so you can see it's a very complicated graph, but first of all, the y, remember the y was wind speed, so the y cannot be negative. So this side, the other side of the graph, we don't even care. That is not part of the domain that we're interested in. For us, wind chill, the wind itself has to be some positive or a zero number. So it is this side of the graph that we're interested in. And then you can see how the shape of the graph changes as the temperature increases or decreases and the wind increases. So studying this graph can tell you what's going to happen if the temperature drops by 1 degree. How is the wind chill going to change? So we will be looking at that. So for us, we're going to start with the functions of two variables. So a function of two variables will be a rule that assigns to each ordered pair of real numbers in a set D a unique real number denoted by f of x, y. And then that function will take some values. It doesn't have to take all the possible values in the real numbers. So we usually write this as follows. So we have in math, we write these functions f. They are functions that take values in the domain, and they give you values in the real numbers. So for every value in some domain, like the wind chill, it doesn't have to be defined for negative values of y. The domain can be restricted. We'll give you some value, which we call f of x, y. Now, we don't have to get every single possible value of, in this case, the temperatures. There's a limit to the absolute zero, so I cannot go below the absolute zero. So there is a value, there's some range of values that can happen. So the domain is precisely what values I can actually evaluate on, while the range is those numbers, let's say, what's a good number? Alpha, real numbers, such that alpha is equal to some value of the function for some actual numbers x0 and y0 that are in the domain. If the value is not in the domain, that is not in the range. Let's see some examples of how this works in practice. So for example, we want to sketch the domain of the function and evaluate at 3,2 if 3,2 is in the domain. So this function is, where is it defined? So the domain in here is the largest set of real numbers where I can evaluate and make sense out of this function. What are those values? When x is 1, so definitely we have to be careful that x is not 1, right? And what else? Yes, I'm going to write it as x plus y plus 1 is bigger or equal to 0. So, right, at some point in your lives, you'll get to complex numbers, but here we're working with real numbers. And when you take the square root of a negative number, that is meaningless over the real numbers. So we need also, for the numerator to make sense, we need for x plus y plus 1 to be bigger or equal to 0. What are those points that satisfy these two conditions? Well, to draw this inequality, what I usually do is, this is going to be some set of points in the xy plane. And what I want is, I draw first the equality, x plus y equals 0. X plus y plus 1 is 0. That is y is minus x minus 1. So that is a line of the slope minus 1 that goes through 0 minus 1. So if here is minus 1, it is this line. Okay? Now evaluate this line, or this, evaluate this quantity at some point on one of the two sides. So for example, at the origin, I get something positive. So by continuity, it is actually positive in the entire, on this entire half plane defined by that line. So I want that half plane so that x plus y plus 1 is positive, but I do not want x equals 1. So I have to exclude that line. Okay? So that is what the domain is going to look like, is all of this and all of this without the line x equals 1, and not here. Not here, and not on that line. Oh, I have to evaluate at 3,2. It's 3,2 in the domain. 3, 1, 2, 3, 1, 2. It's somewhere here, 3,2. That is in the domain, so I can evaluate. F of 3,2 will be the square root of 3 plus 2 plus 1 divided by 3 minus 1. So that is the square root of 6 divided by 2. I can plug in. I get a real number. We're good. Now, for the domain of this function, I just have to make sure that every term in this function is defined. So at what points this function will be well defined. Where can I evaluate? What are the problems here? Where is the logarithm defined? Greater than 0, strictly greater than 0. Okay, so the logarithm of x, that is only defined for positive values of x. Okay? So I need the inside of the logarithm to be strictly positive. In the previous one, the line was included. Okay, so the line itself, the border here was okay. That's when the root, inside the root is 0, the square root of 0 is 0, so it was okay. But here, the border is not going to be okay. I cannot evaluate the logarithm of 0, doesn't exist. So I need y squared minus x to be bigger than 0, which is that y squared is bigger than x, or that y is bigger than plus or minus the square root of x. Again, to graph that, usually what I do is graph the equality, y squared equals x. So y equals plus or minus the square root of x. I know how to draw that. Those are just the square root. And the minus the square root is like that. And now pick a point in one of the sides and see if it satisfies the inequality. So I'm going to pick, for example, here, when x is minus 1 and y is 0, it is a-okay, because when y is 0 and x is minus 1, it's logarithm of 1, which is 0. So it is valid on the left of this parabola. So the domain is all of that region, except that, as I said, we do not include the parabola itself. The parabola itself is already bad. I can get as close as I want to the parabola, but not evaluate at the parabola. So that was a sketch of the region, and I can evaluate at 3, 2. Can I evaluate at 3, 2? Let's see. 3, 2 is 1, 2, 3, 1, 2. Ooh, I don't know. My graph is fuzzy. So let's see. At 3, 2, I get 9 minus 2 is, no, at 3, 2 is 4 minus 3 is 1. So yes, it does work. So 3, 2 is in the region. I just drew my region pretty badly. So 3, 2 is somewhere here, so it's a point that is somewhere there. There is, and I can evaluate at 3, 2, which is the value at that point. It will be 3 times the logarithm of 4 minus 3, which is 1, and the logarithm of 1 is 0, so the value is 0 at that point. Right, now find the domain and the range of the function, the square root of 9 minus x squared minus y squared. First of all, what is the domain? Where does this function make sense? Like before, inside the square root, we want it to be positive or 0, so non-negative. So I need minus 9 minus x squared minus y squared to be bigger or equal to 0. So I want 9 to be bigger or equal to x squared plus y squared. Again, let's see what the actual boundary of this region is. It's 9 is equal to x squared plus y squared, which is a circle of radius 3. Okay? And then it is okay in the boundary because when it's equal, I actually get 0. The square root of 0 is 0. What about, is it the inside that is okay? Is it the outside? Inside is, for example, this point is inside the origin. And at the origin, I get the square root of 9, which is 3. The value here is 3. So it is actually this region that satisfies the inequality that I want. So that is the domain. It's a circle of radius 3, including the frontier. What about the range? Anybody say something about the range? What values can I get with this function? 0 to 3. How do you figure out that the values are from 0 to 3? So this is definitely a positive number. This square root is a positive number. I think what you're trying to say is that the highest value happens right here, and it's 3. And then the value decreases to 0 at the boundary. How do we actually prove that? Let's write it as follows. I'm going to write z, or the values in the range, are those that satisfy that the square root is z values that are equal to the square root of 9 minus some x squared minus some y squared. If I simplify that, what I get is that z squared is 9 minus x squared minus y squared. And what this represents is x squared plus y squared plus z squared equals 9. Okay? And that is the equation of a sphere of radius 3. So over this, the graph is going to be a sphere of radius 3. So the farthest away we can be from the origin in the z direction is 3. Otherwise, I can look at the inside of that function, 9x minus x squared minus y squared, and see that I need this to be positive, or 0. And because x squared and y squared are positive numbers, whenever I plug in some numbers, I'm going to get things that are less than 9. So the inside of the function is at most 9. And when I take square roots, I get that the values of the function are between 0 and 3. So the range is actually the interval from 0 to 3, and it includes both the 0 and the 3. I can reach both values. Now, we're going to also want to sketch graphs. We'll come back to the graph of that square root. But let's try to start with a simpler function. Some functions we're going to graph because we're going to recognize it as things we have already looked at. So how do I sketch that graph? I write z equals 2 minus x minus y, and then try to see if I can identify this equation with the equation of a surface I know. If I bring everything to the left-hand side, I get x plus y plus z equals 2. Do you recognize that equation? It is not a sphere. It's a plane. And what can we know about this plane? Remember, we've seen that the equation of a plane, this is the linear equation of a plane, tells me what is it perpendicular to. So from the coefficients of x, y, and z, it tells me it is perpendicular to the vector 1, 1, 1. And it goes through some points. It goes through the points, for example, I can just plug in x equals 2, put y and z equal to 0. So for example, through the points 2, 0, 0, 0, 2, 0, 0, 0, 2, it goes through all those points. So if I want to sketch this graph, I can just sketch this plane. So this is 1, 2, 1, 2, 1, 2. Draw the triangle. So the graph is actually just some infinite plane, but it's the plane that contains that triangle that passes through those 3 points. That's the graph of the function. And what I've done is identify some surface I knew already to do that. The points I try to find easy points. Okay, I want this to be 2. So well, x could be 2, and these could be just zeros. So I'm just like trying to find points that are easy to see, oh, that point is on the plane. I needed 1 point, in fact, because I know the perpendicular vector, I know 1 point, and from there I can draw the entire thing. But having 3 points allows me to draw a triangle, and it looks better, more sensical in 3D what shape we're talking about. What about the graph of this function? We've already talked about this. I do the same process. I start with the z values are the square root of 9 minus x squared minus y squared. Square, z squared is 9 minus x squared minus y squared. And then bring everything to the left-hand side, or the variables to the left-hand side, and I get this equation, which, as I talked about before, it's a sphere. So the graph of that is a sphere of radius 3, like that. right? That's the graph of what's in yellow. Is this the graph of the function? Is this sphere the graph of my function? It is not a graph of the range. Remember, the range was from 0 to 3. And somehow there are points here that the z coordinate is -3. Yes?
You have to check that the points in your graph are the domain and range.
They have to be in the domain and range of the function. So somehow this part, the bottom half, got introduced in my graph, and those are extraneous solutions which came about when I did this. Okay? If you go to the internet and just Google proof of 1 equals 0 or proof of 1 equals to 2, there's a lot of nonsense proofs, and like 99% of them come about because somebody squared at some point or multiplied by 0 at some point. But when I squared my equation, I actually introduced the negative values also of the square root, the plus or minus the square root, and somehow I introduced this part. But the graph itself will be just the top hemisphere. It's just, this is the graph. This is that sphere. The graph is just the top hemisphere. We also know that this is not a graph, because when I intersect, just like remember in one dimension, do I have some room somewhere? Let me do it here. How do I know this is not a graph of a function of x? Because there was a vertical line test that any vertical line can only have one intersection. This has two, right? A graph in 3 dimensions, when x and y are the variables, can only have, whenever I do a line, a vertical line, it can only have one point of intersection, but this one has two. So it doesn't pass the vertical line test, which is also a rule for functions of 2 variables. Okay? So this cannot be a graph. This cannot be a graph, and the graph is this. And once I remove the bottom half of the sphere, it does pass the vertical line test. How are we going to do graphs of more complicated functions? Something with a logarithm, exponential, sine, cosine. We're going to just do cross sections like we did in the case of quadrics. So I have a function, some f of x, y, okay? And that is z equals f of x, y. Those are my values. And what I'm going to do is I want to draw my graph. First, I'm going to do the cross sections when I put z equals a constant. Those are called level curves. And those are going to be my cross sections that are parallel to the xy plane, but those have a special name, which are level curves. So z equals a constant gives me curves constant equals f of x, y, which is going to be some graph in the xy plane. And it can be, this can be something that is not a graph of a function because it's a curve. And that's just going to tell me that the graph looks like this in the xy plane. And as I move the k, so if this was for k equals 0, that's the graph. For k equals 1, maybe it is going to be some other level curve. It's smaller like this, and that tells me that at level 1, that is the graph. And then I'm also going to do cross sections. I'm going to sometimes also just do the main cross sections. So for example, I pick x equals 0, and then what I get is z is equal to f of 0 comma y. And when x is 0, I'm drawing something in the y-z plane, and suppose that in that it just looks like this. What that tells me is that it's going to look like this in the yz plane. And I can do more cross sections to figure out what it looks like, what my graph looks like by using level curves and using cross-sections, as many cross-sections as I want. And that's how we study graphs in general that are much more complicated than a quadric surface. You've seen level curves before. I took a topographic map of stores, and then you can see, if you've seen these are level curves. Let me draw in purple, for example. So the higher elevations, like if I draw this is the cross section with the with the map at 745 feet. So when k is 745 and f of xy is the elevation in feet at point x comma y, and I'm putting let's put the origin of coordinates at Austin, 108, then my function is telling me what's the elevation in every direction. And the curves are going to tell me, like the different, when I take now k is 710, it's going to tell me those cross sections is what happens like this, because then I know what are all the points that are at one same height. Okay, so these topographical maps are level curves of whatever the surface is, which is the actual surface of the Earth. Let's try to sketch the graph of a function that is a little bit more complicated than what we've seen before. So this graph is not going to be the graph of a quadric, but I start the same way, e minus x squared plus y squared equals z. And then I'm going to start by taking level curves. What are the level curves? I'm going to start with, take z equals k. So k is equal to e minus x squared plus y squared. And let's try to get rid of the e by taking logarithms of both sides. I get logarithm of k is minus x squared plus y squared, which is x squared plus y squared is equal to minus the logarithm of k. What curves am I getting as level curves? They are circles, but you have to be careful because, as we said before, the logarithm is not defined for every value of k. So for example, when k is negative, what happens? I can't evaluate the logarithm. Yeah, you were going to say?
It's a half circle.
No, they are circles. What I'm saying is that you have to be careful that this is not, for example, a negative number, or that the logarithm itself, maybe I can't even evaluate at some numbers. When k is 0, the logarithm would be minus, it would be minus infinity, so it just becomes infinite, a circle of infinite radius. So it doesn't even make sense. And in fact, the exponential function is always positive. So this is always a positive number. So there is no z values that are negative. So we have to have k. We have to have it so that I can evaluate it. So k has to be bigger than 0. So there's only level curves for positive values of k. And also, the logarithm looks like this. This is ln k. So the logarithm of minus ln k looks like this. So as k increases, I'm also going to decrease in radius. And in fact, right here, when k is 1, the radius is 0 and then becomes negative radius, so there's not going to be any points. So what's happening is that I get at k is 0, at k is 1, at height 1, I get exactly 1 point. It's x squared plus y squared equals 0. So there's only 1 point, which is the 0, 0 point. So the first level curve is just right there, and this is for k equals 1. as I decrease the k between 1 and 0, it's actually going to give me bigger and bigger radii, and they're going to grow at an exponential rate. They grow at an exponential rate as k decreases. So what is happening is that the cross sections or the level curves are circles. It starts with a very small circle, and then it just becomes a very large circle. So it's like one mountain. Okay? So let me just draw it here. I'll erase it. But it is something like it's going to be something like that, the graph of that we had before. You can also do cross sections in other directions. So, for example, if I did, just to help me out, what is happening when y is 0? I get z equals e to the minus x squared minus 0. So I get e to the minus x squared, which is the bell curve. So that's why in the cross sections, the main two cross sections in the x direction and y direction, I get bell curves. So that's why it looks sort of like this. Let me sketch it for you. So how much is e to the minus x squared minus y squared? Remove that one. It's a plane? What happened? I have to zoom in. You can see the level curves there. And once I am at least at level 1, then I see the tippity top of the mountain. And then if I zoom out, then I see it sort of like that. It's sort of like a three-dimensional bell curve. So what are the level curves for a function now that has 3 variables? If I have 3 variables, now the level curves are no longer curves, are surfaces. Okay? So I can write this as, let's say these are t values. And then the level curves would be what happens when I fix a t value. So when I fix a t value, for example k, then I get a sphere, and as that k changes, it changes the radius of the sphere. So a function that has 3 variables, x, y, and z, then I can think of the result as the t values as what happens with respect to time, and then it tells me as t changes is what happens in time. So I think of these 4-dimensional objects as 3-dimensional objects evolving in time. So what's happening here is that the level surfaces are spheres of different radius. So for example, well, a t equals 0 is just a point, a t equals 1 is of radius 1, a t equals 4, a t equals 9 is just spheres of different radii. So the level curves are level surfaces, and each one of those surfaces are actually. I wanted to show you that I'm not going to play it here, but I just wanted to point out I made a video about how Aristotle showed that the Earth is spherical, how he gave evidence that the Earth is spherical using cross sections. What he did using cross sections is just suppose the Earth is some object, some surface. So suppose it's something like, I don't know, like a potato or something. Okay. And take cross sections of it. And suppose that I knew that every cross section of the Earth is a circle. Then in that video, I showed you the proof that a surface such that every cross section is a circle. You can see that this one cannot be what we are looking for because the cross section in that direction is, like a pear. So it's not a circle. That can't be Earth. So if every cross-section of Earth is a circle, then Earth needs to be a sphere. Aristotle didn't go and cut Earth in many places just to see that he got circles. What he did was looking at eclipses. If you have the sun, and you have Earth, and you have the moon somewhere here, okay, then the sun is far enough that the shade you see in the moon is equivalent to a cross-section of Earth in that direction. And here you can see that thanks to an eclipse, I'm seeing that this cross-section is a circle. But as we move to different places of Earth and we see that every eclipse is a circle, what he is deducing is that every cross-section of the Earth is a circle. And then there is a theorem in geometry that tells you that if you have a surface that every cross-section is a circle, it has to be a sphere. So that was his argument back then to prove that Earth was a sphere using cross-sections.